73. 73, somebody was asking about that before. It's just using, it's using that that inequality again from last time's. You do not have to have that inequality memorized. It won't show up on the AP test. It won't show up on my test. This book just likes that inequality, so they like to put problems that use it. But you're going to use that inequality. I tried it first, comparing it to a P-series, but I wasn't really getting anywhere with that. So going back, just because I know this book likes this inequality, going back to this inequality, it's that whole thing. So do you want me to walk through that? Okay. You like it? Oh, you don't like it? Do you need me to explain anything? You just don't like it? Okay. Can you explain it, please? Yes. Okay. So let's use this inequality. And actually, let me remember we're trying to find something to compare this to. So we're going to use this inequality to kind of start with. So I'm not showing my work of how I got here, but I'm basically going through the same exact thing where that I did with number 33, where I basically am doing the same stuff, except imagine this is A. So that's still an A. And then I all I need to do to make this pretend this isn't here. So all I need to do to make this guy look like this guy is just put the denominator on. So putting the denominator on, I get this. But again, imagine this is still an A. And then you can make an inequality. I lost my train of thought. You can make an inequality to make it like a P-series and figure out what values of A will work. So I don't remember what values I end up with, but if A is 1/3, it fits into that inequality. And then once we have that, then I went ahead and used the limit comparison test and was able to figure out that it converges. So I take this guy. We know this guy converges by the P-series test. And then I use the limit comparison test to figure out that this thing, this guy right here, can also converge. And then finally, by the comparison test, I'm able to get this. So it took several steps to get there. Yes, Adon.
So A could have been anything below 1?
I don't remember what the inequality was, but yeah. I mean, do you want me to figure it out, or?
I mean, I just want to know what everything is.
So, need a pen. So if that was A still. Now, I'm thinking about the P-series eventually. So this guy has a lower degree than this. So I'm going to kind of ignore this one. So I'm going to think about n to the a minus 2, or 1 over n to the 2 minus a. And then I want that, because this guy is bigger, this thing is bigger, I need the bigger one to converge for the inequality to go the right way. So in order to converge, this has to be bigger than 1. So 2 minus a has to be bigger than 1. Negative a has to be bigger than negative 1. So a is less than 1. If I did my math right real quick. So there's my inequality. Any questions? So yeah, that sounds like what you said. Yes?
57. Why did you make n bigger than or equal to 2?
Just because, so I must have did this a while ago, but it must be because the inequality didn't work at 2. No, it would have. Natural log of 1 is 0, so 2 would be bigger. I'm not sure why. Maybe I had on the brain that I didn't think it was going to work. But yeah, it should. Because if natural log of 1 is 0, then natural log of 2 should be positive. So if I started at 2, this is still just... Oh no, it would be something less than 1 though. That was the problem. Natural log of 2, I don't know what it is, but it's something less than 1. Because natural log of e is 1. And 2 is less than that, so that's why.
And we can assume that if it converges, read it off the reflection.
Yeah, because all this does is just add one more term on.
Yeah.
So, yeah. Any other questions? Yes, Greg.
For this one, did you mean comparison test?
Oh, yep, you are right. All right. Well, let me have your homework, and we have. It's a little bit of a challenging reality check. Actually, it's just one of the first one is kind of just gonna make it. Give you a little extra time. I'll give you 30 more seconds. Okay.
Thank you!
And thank you. All right, so this one is, there's 3 questions. Like I said, the first one's going to take a little more time to think about. I think 8 minutes, though, will still be long enough for the whole thing, because then the other 2 aren't as bad. But I'll check in at 8 minutes, and if it's looking like a lot of people need more time, I'll give more. But let's shoot for 8 right now. Does everybody have one? Too small? Is that too small? You want me to make it bigger and just look at it piece by piece? Now, I'm not saying those are the only tests you could have used. That's just what I used. Any question? Oh, Sid.
Yeah, so for example, for like B, is it legal to take the, like just as an example, like is it fine to take out the 2 in the top outside of the summation
Yep. Totally legal. Any other questions on this one? You ready for the next one, or you want to still look at it? Here's number 2. Hi! Everybody's here, so whoever it is should be here.
Okay.
Hey, look, she's here. Any questions on this one? Ready for number 3? Number 3 was just a geometric series, but kind of on steroids. So remember the formula for the sum of an infinite geometric series, as long as the absolute value of r is less than 1, it's the first term over 1 minus r. This is a fun reality check, wasn't it?
Was this a hard one or
The first one. This one actually shouldn't have been hard if you remembered the formula. A little time consuming, but not too bad.
I remember actually.
Yeah. Oh. I got tissues. Okay. Yes. Yeah, so if the terms tend towards 0, well, the divergence tells us if they don't tend towards 0, we know it's going to diverge. But we can't conclude anything else from the divergence test. We cannot converge that, or we can't conclude that it converges, so that automatically eliminates this one. Just because the terms tend towards 0 doesn't mean the infinite sum is going to be 0, so we can get rid of that one. As far as this goes, does not diverge. I mean, this could be true, but it doesn't have to always be true. Again, the divergence test on this case isn't going to tell us anything. This series could converge or diverge. We don't know anything based on just this. And you can think about p-series to kind of convince you about that. The terms don't have to be positive. They could be negative. So none of the above. Any other questions? Yeah, right. Well, let's take some notes. Yeah. We're going to do section 10.4 today. We're only going to learn one test today. But there's other stuff.
What is the reality check?
Oh, no, but it's on the wall. Let me look. March 7th. All right, today we're going to do something called absolute and conditional convergence. That's the actual title of this section. But also in this section is something very important called alternating series. And if you're one of those people that uses the titles of the section to go back in your notes and find stuff, you may want to look up alternating series, and it won't be in the title. So anyway, there's that. So let's start with alternating series. What is an alternating series? Alternating series is just where the terms alternate in sign. Positive, negative, positive, negative, positive, negative. That's it. So you will typically, not always, there's other ways to get the signs to alternate, but typically what you end up seeing is something like a -1 to some power. So if n starts at 1, this particular series would start at -a⁻1 plus a⁻2 minus a⁻3 plus a⁻4 minus da-da-da-da, and it just continues. Or you could see -1 to the n plus 1, and that would just start us off, as long as n is starting at 1 again, starts us off at a positive term instead, but the terms still alternate. Can't write a plus sign. That's all an alternating series is. An alternating series is not something like this. If you have like a⁻1 plus a⁻2 minus a⁻3 minus a⁻4 plus a⁻5 plus a⁻6 minus a⁻7 minus a⁻8 plus da-da-da-da. So that is not alternating. Every other sign has to change. So that's what I mean by an alternating series. Any questions what an alternating series is? So then, let us look at what the alternating series test is. It's a very easy test. Just only works on alternating series. Alternating series test. Assuming you have something like above. You either have something like -1 to the n times a⁻n, or -1 to the n plus 1 a⁻n. Whether you're starting at the positive or a negative term. But it's an alternating series. Then, if a⁻n is decreasing and approaches 0, so looking at the positive part of the argument, if it's decreasing and approaches 0, the series converges. There you go. That's the alternating series test. So very easy. Yes, it.
So if one of those conditions is not met, it's inconclusive, or can you defend?
I believe it's inconclusive, but I am actually having a brain fart. So hold on 1 second. I'll make sure I don't tell you wrong. Yeah, inconclusive. This has another name, the alternating series test. Also known as the Leibniz test. Leibniz. Our book calls it the alternating series test. Other textbooks might call it the Leibniz test. You can call it whatever you want. Either one of those is fine. And they would know it on the AP test. So yes, it is shorter to write Leibniz than alternating series. So, let's look at an example. Example, determine if the summation as n goes from 1 to infinity of -1 to the n plus 1 times 1 over n converges or diverges. Take a moment to think about that. Anybody have an idea based on the alternating series test if it converges or diverges? Look.
Since 1 over n approaches 0, it converges.
You're missing one thing from your reasoning.
And it's
Yes, that is exactly it. Yeah, like literally, once you've determined you have an alternating series, and this right here tells you it's alternating, look at this part. Is it decreasing? Yes. Does it approach 0? Yes. The series converges. Yay! Like, it's literally that easy. Yes.
When you say decreasing, does that mean it's positive and going this way?
Actually, well,
Or like a magnitude?
yeah, I guess positive, because I was going to say we don't have to have a positive series this time, but yeah, if you're taking the sign out of the issue, then yeah, this is always going to be positive. So yeah.
Okay, so what if it was negative 1 over n?
It would, because the negative you could factor out and put it into here.
So why does it have to be
You assume that all of your negative signs get put in here. It just... The kind of standard way of looking at the alternating series is that this part, the part that's in place of a sub n, is always positive. We don't. I mean, it's not that it has to be necessarily, but like we just kind of go with that. It's kind of the standard way of looking at it. Because if it was always negative, then you could pull out the sign.
Yeah, okay. So like
It couldn't be sometimes positive and sometimes negative, unless the signs alternated. Like, you know, once you pull out because of the nature of alternating series, your negative signs are automatically incorporated into here, and so we say that this is the positive part left.
okay. But like the decreasing part isn't actually like essential, right? Like you can have something that's increasing towards 0 and it can still the a sub n.
I mean, technically, yeah, you could, but it starts to muddy the waters. I mean, it's much clearer if you just say that this is decreasing, approaches 0, because it kind of takes into account that all your negatives are going to be here. But you're right, you could look at it that way. Kieran, looks like you want to add something to this.
1 over n becomes negative, then it just becomes -1 to the n times 1 over n, right? Because it just starts from the opposite, like starts with the opposite sign.
Mhm.
So you can always just
You can always rewrite it as one of these. Yeah. You guys are both kind of saying the same thing, but it's just, yeah. So you're right, Loic, we just typically don't. Because it's just much clearer that your negatives are all in here, so this is just the positive part. We just leave it like that. But you would not be wrong. Let's write this down, though. Let's write it out. So, n equals 1 to infinity, -1 to the n plus 1, 1 over n. So what you do need to say is you do need to establish you have an alternating series, and you need to determine the a sub n part. So this is an alternating series. And you don't have to call the 1 over n a sub n. I mean, you can. But the key thing that you want to say is that 1 over n is decreasing and approaches 0. And then That's it. You're ready to state your conclusion. Therefore, the series, and in this case, since there's only one series in question, you can say the series, but you can also specifically name the series. The series -1 to the n plus 1 times 1 over n as n goes from 1 to infinity converges by the alternating series test. So it's very nice and convenient to be able to do that. Just say that. So that's the alternating series test. Handy. It is handy. Doesn't always work, because obviously if it's not alternating, you can't apply it. But that's another nice thing about it, is it's easy to know when you can apply it, because you'll be able to easily see if it's alternating or not. One little note. Any questions about that, though, I guess, before the one little note? So remember the harmonic series. Which is 1 plus 1/2 plus 1/3 plus 1/4 plus da-da-da-da-da. Did this converge or diverge? It diverges, that's right. But the alternating harmonic series is what we just were working with. If you were to expand out that series we just were working with, it would be 1 minus 1/2 plus 1/3 minus 1/4 plus da-da-da-da. And we just concluded that this guy converges. A little trivia for you. The next time you're at a party and you want to impress somebody, you can just pull out this little fact. This is what you guys talk about, right? Of course. All right, so that's really, oh, actually, no, there is one little thing with alternating. Anybody still need any of this? What? Okay. There is an error bound with alternating. But luckily this formula is super easy to remember. Trust me. Trust me. You switch colors. I don't know what that... Oh, do you still need it? We have enough here. Okay, so we're going to talk about the alternating... You'll hear it actually called... And actually this is true for error bound in general, but alternating series remainder. But it's also a way of looking at error bound. Or really, it's the same thing. It'll make sense when I put it up here. So when you guys are looking at this blue sheet, which, by the way, I realized, Simon and Alicia, I forgot to give you a blue sheet. I have one that I'll give you after the notes. But on the blue sheet, you may have seen remainder in this last column. It's just error bound. So the alternating series error bound is simply this. Remember S without a subscript? That stands for the infinite sum. But when we put a subscript on it, that's partial sum. So S is adding all the terms up to infinity. And then S sub n is just adding n terms. This will always be less than or equal to a sub n plus 1. And that's it. I'll explain it better with an example in case you don't see it. But let's take a look. Example. Let's first start by approximating. So approximate the sum, which is defined by this infinite series as n goes from 1 to infinity, -1 to the n plus 1 of 1 over n factorial using the first 6 terms. I'm grabbing a calculator. I know, a calc cheater. I can't do it in my head. All right, so first 6 terms. That's pretty straightforward. The first term we're going to start at a positive. So the 6th partial sum is starting at positive 1 over 1 factorial, then it's negative 1 over 2 factorial, positive 1 over 3 factorial, and so on, until we get to that. Which, let's see here, 1 minus 1/2 plus 1/6 minus 1/24 plus 1 over 120 minus 1 over 720. Which is exactly equal to 91 over 144. But if you want a decimal approximation, actually it's repeating, so we can say 0.63194 repeating. Now that's not the actual sum, that's just adding the first 6 terms. But how close are we to the actual sum if we could add an infinite number of terms together? Why, that's what the remainder tells us. So, now, find an interval that S, the actual sum, must lie in. So we're just going to use a formula. So the formula I'm just going to write down first. I won't fill anything in. The absolute value of the infinite sum minus the nth partial sum should be less than a sub n plus 1. So the actual sum, we don't know. We just found that the 6th partial sum was 91 minus 144. Or sorry, 91 over 144. And that must equal a sub n plus 1. Anybody know what problem we're going to work out to figure out what a sub n plus 1 is? 1 over 7 factorial, exactly. Which is what I was just doing on the calculator. Actually, let me put this down here. 1 over 7 factorial. So think of it as the next term. It's not really the next term because it's ignoring the positive or negative part. It might be negative. So it's just the absolute value of the next term. And then, now to make this into an interval. So basically this is saying that the error, remember the absolute value part represents the error. So the error in our answer must be less than or equal to this. So this part here is the error, and this part is our error bound. It's just a much easier formula for error bound. The error of our answer is bounded by this number. The error of our answer has to be smaller than that. And then to actually answer this question, because this question wanted an interval, then I can do negative 1 over 7 factorial is less than or equal to s minus 91 over 144, which is less than or equal to positive 1 over 7 factorial. So let's actually say 91 over 144 minus, and 7 factorial is 5040. So here's the interval, and then I'll just work out these decimal approximations. Let's see how good it is. Let's see how narrow this is. So 91 over 144 minus 1 over 5040. That's 0.63174-ish. And then if I just change that to a plus sign, 0.63214. Very small window there. There you go. That's the alternating series remainder, error bound. So isn't that a much easier formula than we had before?
Yes.
All right, so that's alternating series in a nutshell. But we haven't even talked about the title of this section, which is Absolute and Conditional Convergence. Whatever that is. Anybody need this still? We'll go this color. How much room do I have left? I'll go to a new page. We ready now? Okay. Actually, no, I'm going to fit it here. But new topic. So, absolute, we're going to make a bubble. We're going to make a cloud. Absolute and conditional convergence. So that says, if, let's see here, the summation of a sub n is absolutely convergent. Convergent. If the summation of the absolute value of a sub n is convergent. And another way of saying the same statement is that absolute convergence implies convergence. So if you can show that a series converges absolutely, then you know it converges. Which may not make much sense right now, but just go with it. Or, if the summation of a sub n is convergent, but the summation of the absolute value of a sub n diverges, then we say the summation of a sub n is conditionally convergent. And I'm going to show you a video at the end of the lesson to explain this. It's going to be video time. Conditionally convergent. It's a good video, though. Godzilla! So let's kind of investigate this a little bit more, and then we'll look at why this is important to know. I see people writing this down, so I'm going to pause. Pause. Wait. They need like snarky recordings on those their crosswalks. That's what I would like. And I want a snarky GPS navigation system. Right? Dumbass. Now you got to do a U-turn. Like that. I would like that. You can?
Yeah. Well,
How?
On Waze, you can record your voice for like all the directions or any place.
Oh, but then
You can have someone that you really hate do your voiceover. It just cuts you out of everything. And then every time you have your audio on, it tells you to make God your
so if you do that though, and you're like, because I do like it. If I usually have the audio off because it just annoys me. But if I'm gonna have it on, it's because I specifically want it to tell me the street names coming up and everything. Can you still get that, or is it just replace that audio with your?
does just
Yeah.
together the voice the person that gave it to you. Like it could, like I haven't done it before. My sister did it, and it was so annoying. It was the worst.
Oh man. When cell phones first came out with like personalized ringtones, Colin, I can actually see his face. I don't remember his last name now. I had him like 20 years ago, but I recorded on Colin's phone. Colin, do your homework. And then I would call him just periodically throughout the day. Colin, do your homework. Colin, do your homework. Colin, do your homework. I wonder how Colin is. All right. Anyway, before we look at an example, let's just so if a series, if the summation of the absolute value converges, was absolutely convergent, which means the original series is going to converge. But let's make a table out of this to try to keep it all straight. So we're going to have one column that's the summation of a sub n, one column that's the summation of the absolute value of a sub n, and then we're going to put the summation of a sub n again. It'll make sense why I'm repeating a column. And I'm going to use C and D for converges and diverges. So our legend, C equals converge, and D equals diverge. So we have basically 4 ways that this could go. Either both of the series can converge. The first one converges, the second one diverges. Both of them diverge, or the first one diverges and the second one converges. What I want to put in the last column is based on these. Does that mean that the summation of a sub n absolutely converges or conditionally converges? So if both of them are convergent, does that mean that the series converges conditionally or absolutely? Absolutely right. So this, converges absolutely. Okay, what if the first one converges but the second one diverges? That's conditional. Yep. Converges conditionally. What if they both diverge? Yeah, that's neither one. Duh. We just said it in the first column. The first column, it diverges. Okay, what if the first one diverges but the second one converges? It's not possible. Good. Oh. Because, remember what I have up there in green, absolute convergence implies convergence. If the summation of the absolute a sub n converges, that makes the first column have to converge. So not possible. So, your task right now is to determine if the following converge conditionally or abso-freaking-lutely. Don't put that as your answer on the AP test. Unless you're like really lost, really screwed, and you're like, I don't know, I'm just going to try to make the reader, smile and laugh, and maybe they'll give me some points. So one of them is a summation as n goes from 1 to infinity of -1 to the nth. Oops. Well, I'll write it like this. Times 1 over root n. And the summation as n goes from 1 to infinity of -1 to the n over n to the 3/2. So that is your task. I will pause the video right now, give you time to work. All right, let's take a look. So Caleb asked a good question about, do you have to prove both? And so the answer is, it depends. If you take a look at this first one, so the first one, I mean, basically, if you know that this part, like I did both of them, but if you know that this one with the absolute value converges, you automatically can assume the original series converges. You don't have to say that it does. This is enough, because absolute convergence implies convergence. You can just go ahead and take this guy and just say that this would converge. Unfortunately, this guy diverges. So if this diverges, you still have to go back and do this one. So that's why it depends. So this one, the original series converged, alternating series test. But this one diverges because it would be a p-series then that diverges. So we can say it's conditionally convergent. So does that make sense? What you guys doing? Uh-huh. That's a hard word today. And then for the second one, so here you can see an example. So if you start with the absolute value one, that's convergent, which automatically would be enough to just say it absolutely converges. Any questions about that? While you guys are writing this down, so the quick answer of why would you care if a series converges conditionally or absolutely is because if a series converges absolutely, then you can rearrange the terms however you want and be confident that you're still going to get the same sum, whatever it converges to. If the series converges conditionally, you actually cannot just rearrange the terms, which may seem weird, because wait a minute. Can't we just rearrange terms? Isn't like 2 plus 3 the same thing as 3 plus 2? Last I checked, they were both 5. But, yeah, but, right? We don't do numbers anymore. But if it turns out if it's infinite, then it actually does matter. And so the video I'm going to show you is a really good explanation of why it will. So that's actually why we care. If it converges conditionally or absolutely, we can do more manipulation with the series if it converges absolutely. So any questions about this? Does anybody still need this? Okay. Yes.
Last test, we would first look to see alternating and then be able to use put a multiple series test value.
Yeah. This won't make any sense to you guys here because you won't see it. But if you're watching the video at home, you can go to the link in the screen, and that will take you to the video that I'm about to show, but this is the end of the notes.